Section 10.2, the law of sines. Our objectives are to solve oblique triangles by using the law of sines and to use area formulas to find the areas of triangles. So we're really going to focus on just the first part for this video right here, and we'll do the area later. Now, the derivation of the law of sines you can find on your book on page 625 if you want to go ahead and look at that, and we'll talk about it in class as well. But for right now, let's just go ahead and look at the equations that we have. For the law of sines, it's the ratio of the side to the angle of the side opposite the side that you're given. So A over the sine of A is equal to B over the sine of B, which is equal to C over the sine of C. And of course, we can also flip those and put all of the sines on top over the side. So you need to have this memorized, that it's A over the sine of A, B over the sine of B, C over the sine of C, or vice versa. We also talked about the supplementary angle identity, which says that if I know what this angle is right here, I can find the other angle by doing 180 degrees minus that angle. So we've talked about the law of cosines, and for the law of cosines, we were using that when we were given side, 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 and side, angle, side. So that's when we use the law of cosines. But what happens when we're not given side, 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 or the angle in between the two sides? Let's say we have angle, angle, side, or we can also write this as side, angle, angle. Then I have to use the law of sines in order to solve this. So for example, if I have a given angle, a side, so let's say I was given this angle here, and maybe I knew this side here. Well, I can't use the law of cosines in order to solve that. I would have to use the law of sines. I could actually, if I wanted to, use the triangle sum theorem to figure out what this angle is if I have two angles, and then I could go ahead and use the law of sines to figure out the rest. So we'll talk about that. And also, if I have given side-side angle, you're going to use the law of sines, and this is what we call the ambiguous case, and we'll talk about what that means in a little bit. So let's just go ahead and do two problems first. The first thing you always want to do when solving these is make yourself a triangle. So if B equals 20 degrees, C equals 31 degrees, and B length is equal to 210, find the other angle and side measures of ABC. So the first thing I did was draw myself a triangle. So we have angle measure B is 20 degrees, angle measure C is 31 degrees, and we know that length of B is 210. So now we want to find the other angle measures in triangle ABC. So for this one here, I cannot use the law of cosines, but I can use the law of sines. So for the law of sines, we can do the sine of 20 degrees over, because this is B, over this side of B, so over 210, is equal to the sine of 31 degrees, sorry, that's a degrees, 31 degrees over, and then we don't know this side, so I'm going to just call this C. So if I want to solve this, I can cross multiply. So when I cross multiply, I get C times the sine of 20 degrees equals 210 times the sine of 31 degrees. And then I'm solving for C, so C is equal to 210 sine of 31 degrees divided by the sine of 20 degrees. So I plug this into my calculator, and if I hit enter, I get C length is equal to 316.23. So that's what I'm going to use. And notice I put parentheses around what's in my numerator versus my denominator. So this C value then is equal to 316.23. Now we found C, now we want to find length A. So I can, now if I wanted to I can use the law of cosines because I have two sides and include an angle. I like the law of sines a lot better. I think it's a lot easier, so I'm going to use that. I also need to figure out what angle A is, and angle A is easy to find because angle measure of A would be equal to 180 degrees minus 20 degrees minus 31 degrees, because remember all the angles in the triangle add up to 180 degrees, which is 129 degrees. So this would be angle A. So now I want to figure out what side A is equal to, and I'm going to use the law of sines. So the sine of 129 degrees over A, because we don't know what this side is equal to, equals the sine of 20 degrees over 210. And notice I used angle B and side B because that was given to me in the original problem. So just in case if I made a mistake finding C, I don't want to use that one in my triangle when I'm solving. So for this one, we cross multiply, we get 210 times the sine of 129 degrees equals A times the sine of 20 degrees. Divide by a sine of 20 degrees, and you get A is equal to 210 times the sine of 129 degrees over the sine of 20 degrees. And again, make sure you put parentheses in the correct places. Make sure your calculator is in degree mode. And when you do this, you get side A is equal to 477.17. So right now I'm going to start measuring angles to the nearest tenth and lengths to the nearest hundredth. So to get our answers to be a little bit more accurate. So let's go ahead and do one more. And I forgot to say in this one, before I even started, I looked and saw that I had angle side, so that's usually helpful to write down as well. So for the next one, it says if A is equal to 115 degrees, B is equal to 27 degrees, and length A is equal to 45, find the other sides and angle measure in the triangle. So we have our triangle. Oops. Like that. So I'm going to call this A because we want this to be 115 degrees. And let's call this B, so this would be 27 degrees. And I'm going to call this C, so we know that over here this is 45, length A. Now, if you notice, you have an angle, and the side, so this is angle, side, which means I can use the law of sines. So for this one, I need to figure out, let's do first what the side B is equal to. So the sine of 27 degrees over B is equal to the sine of 115 degrees over 45. So then if I cross multiply to solve, I get 45 times the sine of 27 degrees is equal to B times the sine of 115 degrees. So B would be equal to 45 times the sine of 27 degrees divided by the sine of 115 degrees. Plug this into your calculator to make sure you can get the same answer, and when you do, you should end up with B is equal to 22.54. So why don't you guys pause it and see if you can figure out the rest, and then unpause it and we'll look at it together. So angle C is going to be 180 degrees minus 115 degrees minus 27 degrees, which ends up giving us a value of 38 degrees. And then I need to lastly find what length C is equal to. So I'm going to again use the law of sines for that one. So the sine of 38 degrees over C is equal to the sine of 115 degrees over 45. And notice I used the given angle with the given length that I had from the beginning to make sure, in case I made a mistake, I don't mess up. So then for this one, I get 45 times the sine of 38 degrees equals C times the sine of 115 degrees. So C is equal to 45 times the sine of 38 degrees over the sine of 115 degrees. And when you plug this into your calculator, you end up with C being equal to 30.57. So now I have length B, length C, and angle C. So now I'm done. Now, these problems tend to get trickier when we start to do other things, such as a side, and an angle. So side, angle is what we call the ambiguous case. So why is it ambiguous? Because you have different possibilities of your triangles. You can have 0, 1, or 2 triangles satisfying the given conditions. So let's say that you are given triangle ABC and that our given angle is going to be less than 90 degrees. And let's say that we're given angle A, side B, and the side opposite the angle, which is A in this case. There's all these different scenarios that we can have. So the first scenario is when you have given this angle right here. So we know the angle, you're given this length B and this side A. And we're saying that that side A is smaller than B and it's smaller than the height of your triangle. If this is smaller than the height of your triangle, if I were to take this length and circle it around, it would never reach this other side that we have right here, which is why it's dotted, because we're unsure what the side length is and we don't know if we can complete the triangle. So because of that, the triangles that are going to be possible whenever this length here is smaller than the height are going to be 0 because it's too short to reach. And how do I know what the height of my triangle is? Well, if you think about a right triangle, let's draw a better right triangle there. So if you think about a right triangle, so if we think about a right triangle, the height of my triangle would actually be the opposite side, the given angle that you have in this case. So how do you find the height of the triangle? You can do, if we are given angle A, well then I know that the sine of A is equal to opposite over hypotenuse. So instead of saying A here, we're calling A our H. So A equals H. So this would be H now. So if I wanted to solve for the height of my triangle, the height of my triangle is going to be equal to B times the sine of A. So really it's the length that's not opposite the given angle and the sine of that angle. So this is how you find the height of your triangle, which is going to help us solve these and figure out how many solutions that we have. So in this case, if I were to do B times the sine of A, it's going to be equal to a value that is less than the height. And so because it's going to be less than the height, then I know that this side A right here is never going to reach. So whenever that A value is equal to the height, there's only going to be one possible solution because it's going to make a 90-degree angle when it's the same as the height of the triangle. And then when we have something like this, so again, and this I should have said up here, this is your C value, which is an unknown angle. We don't know what that angle is, which is why we can swing the A value. And this down here would be B, which we don't know what the angle for B is either until we figure out the triangles. So in this case, if this is C, this would be, I'm going to call this B1 or B2. So for this triangle that we have here, notice that in this case, A is bigger than the height of the triangle, but it's less than length B. If that's the case, then you're always going to have two possible solutions. And when this length that's given A is longer than the height of the triangle and also longer than this length B, there's always going to be one solution. So I want to go ahead and take a look at some of these scenarios. So again, the first one was when the length A that we have is going to be less than the height of the triangle. So in this case right here, we have a right triangle. So the height of my triangle would be right here. So we're saying that we are given A, which is equal to 30 degrees. We are given side B, which we're going to say is equal to 20. And length A is equal to, and we're going to change that around, so this is our unknown for right now. So the height of this triangle would be equal to 20, so you always use the side that's not opposite the angle, times the sine of 30 degrees, which is actually equal to 10. So in this case, when our A value is equal to the height, which is what we have right now, so we are saying right now that A is equal to 10. Notice that I have this right triangle when that's the case. So now let's say that our A value is going to be less than the height. So if this A value is less than the height, so I'm going to take this value, move it here, notice that no matter where I swing my angle around to, so we're saying that we could move this here or here, and anywhere I swing this around my circle, that A value, it's never going to reach the other side of my triangle. We will never be able to reach this side right down here. So because of that, there are no possible solutions. So anytime that A value is less than the height of my triangle, it will never ever reach the third side until we get to the value where it makes a right triangle. So where it is equal to. Now I have one solution. So then the next case scenario is when your A value is greater than the height, but your A value is less than your given length of the other side. So in this case, notice that here, let's say I have, let's do a nicer value. So let's say I have an A value of 12. If I have an A value of 12 and I were to swing that around my circle, notice that it would hit right here on the third length, and it would also hit right here on the third length. Anywhere else I try to swing that length that we have for 12, it won't hit. So because of that, notice that we have two triangle solutions of where my graph is hitting. So even if I change it, so if I keep going, two solutions, two solutions, two solutions, two solutions, but as soon as I am equal to that B value, so as soon as I'm equal to that B value, notice that I only have one solution. So, and the only triangle solution that you can have would be in a triangle that looks something like this. So that would be if your B is equal to your A value, and if it's greater than that B value, anytime it's greater than that, notice you're only going to ever have one solution. So those are the different cases that I was just talking about. So it's really helpful to know the height of your triangle when you're doing this, because if you know the height, if that other side opposite that given angle is shorter than the height, then again, you have no solutions. When it is equal to the height, which is right here, you have one solution. When it is bigger than the height but less than your B value, you have two solutions. And when it's greater than or equal to that B value, you have only one solution. So those are the different scenarios. And I'm going to leave this applet on my, a link to it on my website so that you guys can kind of look and play around with that as well. So that's where these triangle solutions come in handy. Now, what happens when our angle that's given is not an acute angle? Let's say now it is an obtuse angle. Or an angle that's greater than 90 degrees. So if that is the case, now the height of our triangle is measured by this distance here. And so for this, if your A is greater than your B value, you're always going to have one possible solution. If your A is less than B in this case scenario, then you're going to have no solutions, because no matter where you swing that A value around and try to put it, it will never ever reach the third side of your triangle that you have. So even just to go back to the applet that we had, I think we can show that. So if I make my A value, so here's my obtuse angle, so we're given that. So if I have my B value equal to my A value, it doesn't make a triangle because then you wouldn't have any angles. But if it's a little bit larger, notice that we would get one triangle. And if it's less than that B value, then no matter where you swing your A value around, it will never reach the third side of your triangle, no matter where it's at. So it has to be bigger than your B value in order for this case to make a triangle. So what happens if we're not given A? So let's say that we were given, so if you're given angle A, and side B, then the height is equal to your length that's not opposite the angle, so B times the sine of A. If you were given, let's say, B and A, then the height would be equal to, in this case, A times the sine of B. If you are given C, C, and let's say B, then your height would be equal to B times the sine of angle C. Let's say instead it was C, C, A, then the height would be equal to A times the sine of C. So notice that it's always the sine of the angle times the length that's not opposite the angle to figure out the height. And again, you just need to figure out if you're, then in this case, you would have to figure out if this value that I have right here, is it going to be bigger than the height, less than the height, or equal to the height for your different cases for your triangles. So let's go ahead and practice some of these. So for this first one, it says, given the possible triangle with side A, side B equals 7, side A was 6, and angle A is equal to 65 degrees, we want to find angle B, and we're actually going to solve to find the rest of it. So in this case, notice I have two sides and the angle opposite one of the sides. So because of that, I know that this is the ambiguous case. We have side, side, and angle. Or if you rewrite that the other way, anytime you have the ASS theorem, it's a pain because you have to figure out how many triangles you have. So for this, always draw a picture first. So I have angle A, which is 65 degrees. So we have 65 degrees for angle A. And we know that this we're going to call B, which is 7, and then we have this side right here, which is 6. So we know that down here would be B and here would be C. So we need to figure out if this 6 is long enough to hit this other side down here of C. So that means I need to figure out the height of my triangle. So to figure out the height of my triangle, it's going to be 7 times the sine of 65 degrees, because again, it's always the length that's not opposite the angle times the sine of the angle. So 7 times the sine of 65 degrees is equal to 6.344. So in this case, notice that my A value is going to be less than the height of my triangle. Because of that, I know that there are no possible triangle solutions for this. So there's going to be no solutions because of that. So that means that that triangle, this length, is just going to fall short of that other side. So no matter where I swing this side around to, it's never going to be able to hit that third length. And let's say you didn't know that. So let's say you thought that there was a triangle and you wanted to solve this. You can even tell when you're doing your calculations that this doesn't work. So let's do the sine of 65 degrees over 6 equals the sine of B over 7. So if I solve this and cross multiply, I get 6 times the sine of B equals 7 times the sine of 65 degrees. So if I solve for the sine of B, the sine of B is equal to 7 times the sine of 65 degrees over 6. So then I'm going to plug this into my calculator. And when I plug that into my calculator, I have, clear that out. So 7 times the sine of 65 divided by 6. And then don't remember, this is not my actual angle because I have to do the sine of that answer. So I have the sine of B is equal to, and I think it was 1 point something, 1.057. Well, remember, now I'd have to take the sine inverse to solve. So B is equal to the sine inverse of that answer, 1.057. And remember, we said before, we can't take the sine inverse of something that's above 1 or below -1. So that means this has no solutions. And even in your calculator, if you try to do that, so if I do the second sine inverse of the second answer, and hit enter, notice it says error domain. Because it's not in our domain, therefore I have no triangles. So that's another way. So even if you forgot how to do this part right here, you can still solve it to figure out, well, there was no solutions because I couldn't solve for the triangle. So another case, let's say we're given triangle ABC with A equals 10, B equals 11, and the angle opposite of A is 23 degrees. So again, this is the side-side angle scenario. So if I draw my triangle, we don't know that length right there that I just drew, but we know that A is 23 degrees. And we were given that B is 11 and A is 10. So I'm just going to draw the triangle right here. So this is 10. So I need to figure out the height of my triangle to see if I can have a solution. So the height is equal to 11 times the sine of 23 degrees. So 11 times the sine of 23 degrees in my calculator, if I do this, I get is equal to 4.298. So that means that side A is bigger than the height, and side A is also less than side B, so therefore I'm going to have two triangle solutions when I'm solving this. So that means that this side would hit somewhere on this length here, and then it's also going to be able to swing and hit somewhere here. So those are my two possible triangles that I'm going to have to solve. So we're going to call that one B1, and this would be B2. So even if I didn't know how to, again, do this, I could still solve to try to see if I have two triangles. So we're solving for B1 first. So I'm going to draw my first triangle scenario, the bigger one. So in this case, we would first solve and you would get the sine of 23 degrees over 10 is equal to the sine of B1 over 11. So cross multiply, and you would end up with the sine of B is equal to 11 times the sine of 23 degrees divided by 10. Don't forget to do the sine inverse on your calculator. So when you do the sine inverse, you end up with B being equal to so B is equal to 25.5 degrees. So if I know now this angle is 25.5 degrees, then I can use the triangle sum theorem to solve for C. So C1, we're going to call it, is equal to 180 degrees minus 23 degrees minus 25.5 degrees, which ends up giving us a value of 131.5 degrees. So this is equal to 131.5 degrees using the triangle sum theorem. So now that we have that, the last length to solve for would be side C, which I can again use the law of sine. So the sine of 23 degrees over 10 equals the sine of C, which we just said was 131.5 degrees, over length C, which is what we're trying to solve for. So C in this case would be equal to 10 times the sine of 131.5 degrees divided by the sine of 23 degrees. That which what you would get when you cross multiply. So I'm going to call this little c1. So little c1 is equal to, or the length, 19.17. So now I have my two angles and my other side. So now that we have case 1, we have to figure out what case 2 is. So when you're solving case 1, you're always solving for the larger triangle first. So this was the triangle that we first solved. And case 2, that's not a very good triangle. So case 2 is when we took that side and we're now swinging it to hit the other side, which would be right here. So now we're solving for this triangle that looks like this. So A stays 23 degrees. This would be, let's call it C2, and we're going to call this B2. So this would be side C2. This is going to be still over here 11, and this is 10. Notice that that inside triangle that we have right here, this actually makes an isosceles triangle because this length and this length are the same. Whenever you have an isosceles triangle, that means that this angle and this angle are going to be the same measure. And we already just found what this angle measure was. We just said that was 25.5 degrees. So if I know that's 25.5 degrees, therefore then this angle has to be 25.5 degrees. And now we can use the supplementary angle postulate that says if I want to find this angle here, well, since this is a straight line, I can take 180 minus 25.5 degrees to find B2. So B2 is going to be equal to 180 degrees minus B1, which in this case would be 25.5 degrees. So when we do this, we end up with B2 being equal to 154.5 degrees. And this will always be the case. You're always finding the larger triangle first when you have two triangles, and then the smaller one next, because it's going to swing in. And you're always going to do 180 minus the first angle that you found. And even just to go back to here, I drew the triangle in. So notice that this is when we have a length of 10 for A, B is 11, and A is 23. And notice that it's a very small triangle, but it hits again here and here. Those are where we got the two different triangles from. So that's what it would look like on that applet. So then now if I have B2, well then C2 would be easy to find, and I should write case 2 here. So C2 would then be equal to, I'm going to take my original A value, which we said was 23 degrees, and now I'm taking B2. So C2 is equal to 180 degrees minus 23 degrees minus what I just found for case 2, 154.5 degrees. So when I do that, notice the angle that I get is 2.5 degrees. So it's very small, but we still have one. And then the last thing I need to do is now solve for this C2 right here for that little triangle, because again, remember, we're solving this triangle right here, which is very small. So for this case, now I have the sine of 23 degrees over 10 equals the sine of 150, or let's do 2.5 because that's our C. So the sine of 2.5 degrees over C2. So when you cross multiply and solve, you get C2 is equal to 10 times the sine of 2.5 degrees divided by the sine of 23 degrees. When you plug this into your calculator, you end up with 1.12 for the length. So this right here would be case 2. So that's how you would find the second case. And just to go back to the applet here, notice that that distance that we have is really small right there. So that's why it's still a triangle even though it's very small. So that's an ambiguous case scenario. So we're going to skip example 5 and go ahead and go to example 6 here. So for example 6, we have C equals 22, B equals 12, and C equals 42 degrees. So I have two sides and the side opposite the angle. So again, it's side, side, angle. So it's the ambiguous case. Now if I draw my triangle, we have C as my given angle. So instead of putting A there, I'm going to put C. So that's 42 degrees. And that means that this over here would be length C, which is 22. And that means this is going to be, I'm going to use this side as B over here because I always like using the same side. So this would be B, and this is now A. So that's what our triangle would look like. So the height of the triangle would now be equal to B, because that's not opposite the angle, times the sine of the given angle, which is 42 degrees, so the sine of C. So, which is really equal to 12 times the sine of 42 degrees. So in this case, I have this is equal to 8.029. And actually, I didn't even need to figure that out because notice that this length here, even though my triangle is not drawn very well, is larger than this length. Anytime this length is bigger than this length, you're always going to only have one solution. So I know there's one solution. But we're going to solve this and say that we thought there was two solutions. So I'm going to show you how to watch out for that. So for our triangle solution, if I'm going to solve this, I want to solve for b first. So the sine of 42 degrees over 22 is equal to the sine of b over 12. So that means that the sine of b would be equal to 12 times the sine of 42 degrees divided by 22. Don't forget to do the sine inverse to find your solution. So b would be equal to a value of 21.4 degrees. And make sure you can plug that into your calculator. So now that I have b, then that means I can find a. A is equal to 180 degrees minus 21.4 degrees minus 42 degrees, which would be equal to 116.6 degrees. And then I can solve for length of A by again using the using our law of sines. So for that side, we would have the sine of 116.6 degrees over A, because that's what we're solving for, equals the sine of 42 degrees over length of C, which is 22. When you cross multiply and solve this, you get A is equal to 29.4. So that would be my triangle answer. Let's say that we thought that there was a second case. So if I tried to do a case 2, oops, let's see what would happen. So I didn't know that there wasn't a second case, but I'm going to try to solve anyway. So case 2 would be, I would be moving this over here, and so if this is my angle B, then this would be B2. So we're going to take 180 minus B1, so B2 would then be equal to 180 degrees minus B1, which was 21.4. So in that case, we would end up with 158.6 degrees. So then if I try to solve for angle A2, so this new angle right here, then I would do 180 degrees minus minus 158.6 degrees minus my given angle, which is 42 degrees. Well, notice if you try to do this, we have 180 minus 158.6 minus 42. And notice that I get a negative angle. I can't have a negative angle. And since I can't have a negative angle, that means that these two angle measures are larger than 180 degrees, which we can't have for a triangle. Therefore, case 2 would not work. So again, if you didn't remember how to do this part here, then you can just try to solve for case 2 and you would see that it would not work because it would be impossible to have a triangle that adds up more than 180 degrees. So bring this with you to class and we will finish that last example in class together.